respected reviewers, member of jury, and audience present here and on the online. Good afternoon, all, and welcome to the PhD defense presentation, which entitles Experimental Analysis of Seismic Vulnerability of Earth Masonry Reinforced with Horizontal Band. This work is funded by EDEX under cross-disciplinary program HITS, and the work has been done in collaboration between two research labs, 3SR, which is specialized in engineering field, and AECC research unit, which is specialized in traditional construction and architecture. So the presentation outline for today is, we'll start with the introduction where I'll talk about the background of the study, the scientific challenge faced in the field, the role of interdisciplinary in this project, followed by the objective of this thesis, which is fulfilled by the multi-scale experimental approach, which is classified into 3 different categories, and finally the results and the conclusion and the contribution of this work will be highlighted. Earth construction is one of the oldest construction technique that is still providing shelter to millions of people around the world. And this type of construction is more common in developing and least developed countries, which also lies in seismically active zone, making them seismically vulnerable to earthquake event. Every year, thousands of lives are lost during seismic event, but actually it is not the earthquake that takes life, rather the building which fails to withstand the seismic load and get collapsed, that takes life. So what happens during the seismic event? During a seismic event, there is a horizontal force acting in the structures, creating different stress scenario for in-plane and out-of-plane wall. And in order to prevent this damage, this effect has to be minimized. There are different approaches available for strengthening the unreinforced masonry structures and minimizing the effect of seismic action. And one of them is horizontal seismic band, which is studied in this thesis. So what is horizontal seismic band? In literature, the exact definition was not available, so we have tried to define a horizontal seismic band as a constructive device, which is specific for traditional masonry construction that can be continuous or discontinuous, depending upon the position of application. And this technique is not new. It has been used for more than 5,000 years now. And still we see the application of such a band with different material around the world. But the documentation of application of such band in guideline and building code is relatively new. It's been 4 decades now, and there are different guidelines which propose and recommend the application of horizontal seismic band in the building code. But among this code, there's a variations in terms of dimension, material used, placement of the band, and it also lacks quantified information regarding how the different material behaves in case of seismic action, which makes it challenging in order to recommend in the field. And in my study, the area of focus is Nepal, so I have referred DUDBC guideline, which is based on the National Building Code of Nepal, National Building Code 203 of Nepal. Nepal lies in a seismically active zone because of presence of 2 tectonic plates, and because of the difficult terrain, it's very difficult for the road transportations. And due to the seismic event in 2015, there were thousands of structures that was completely collapsed. And as a support from the international organization, AECC and Qatar was involved in the reconstruction activity in Nepal, along with the collaboration of local partner ASF Nepal. During this reconstruction activity, they provided technical support and the training to the local community. But not all houses were properly monitored, and people were seen applying different type of band in the same structure without following the guideline that was provided by the DUDBC, which created a challenging question regarding what could happen in case of future earthquake. Because of the active seismic plate, it's only a matter of time when it will occur, but definitely we have to make sure these structures are safe from the future earthquake. And in the field, during the reconstruction, there were various stakeholders involved, and they were not able to address the concern regarding the selection of material, whether it should be used with the timber or with the reinforced concrete, and what could be their performance in case of future earthquake. So in order to address these challenging questions, and the request from the stakeholders, AECC took the responsibility to collect the relevant information from site and collaborated with CSR lab in order to study this behavior scientifically. So in global framework of interdisciplinary, my project PhD research work plays a small role in addressing the scientific challenge that is faced in the field and provide the scientific recommendation for the community and the various stakeholders, which will be later shared among various stakeholders to implement in the site and also get feedback from the community in order to what should be the further research work that has to be carried out in order to address the issue in the field. Even in the core PhD research work, there is the involvement of various engineers and architects, which helped in planning the experiment, designing the setup, and execution of all the experimental work. Now, looking at the state of art that has been done in case of seismic band, the mechanical performance of seismic band has been studied in quasi-static and dynamic tests, but there are only few research work which highlights the advantage of having horizontal seismic band in the structures, and there lacks the comparison between different materials when used as a seismic band. And also in the numerical analysis, there is only a few numerical analysis that has been made, and there lacks proper validations from there is a lack of proper validations from the experimental work.
No problem, continue. Okay. That doesn't matter.
Okay. So to address this gap in the literature, the objective of my thesis is defined. So the main objective is to study the parasitic behavior of horizontal seismic band and compare the result of two materials when used as a seismic band. One timber, another reinforced concrete. This project is a part of global work, which is classified into experimental and the numerical one. My work is mainly focused for the experimental work. And there was another parallel PhD who developed a numerical model for masonry structures, who completed recently, a few months back. And my experimental result was used for the validation of his numerical model. To achieve the goal of my project, we have divided into three different scales of experimental campaign. Scale 1 at material, where the mechanical property of material and the shear resistance at interface is studied. At scale 2, the characterization of the wall is made with regard to capacity, ductility, and the shear resistance. At scale 3, reduced scale house is tested on the dynamic load and compared their performance. But before moving ahead with exploring the result, let me walk you through the timeline of my PhD journey. Since the beginning of 2018, I was involved in development of two experimental setups, shake table and the shear setup. I spent more than 1 year to develop these two setups along with another PhD student. And I also had developed constructed samples to be tested on the shake table and with the shear test apparatus. But there was a fire incident in 2020 February, which destroyed everything. Both the apparatus that was developed was destroyed, and all my samples were completely gone. So there was no any result available. So in order to continue my work, we had to redesign and reorganize all the experimental campaign. So in order to continue my PhD work, we had to design a new experimental setup, reaction frame setup, to continue work at CSR lab. And we are really thankful for FCBA for providing us the opportunity to use their shake table for the dynamic test. And due to several reasons, there were no other option rather than choosing extruded Adobe for our reduced scale model. But this also provided us the opportunity to compare two type of material, Adobe and extruded Adobe, which is compared during the study. And it was very challenging period due to the pandemic and a lot of event that was ongoing. So it was very challenging tasks to be completed in short time of period. So now let's move ahead with exploring the results for material scale. So three type of tests is carried out to measure the compressive flexure and the shear strength of the material. This test is important because during an earthquake event, the structures goes under different stress scenario, creating different stress mode, and this stress can govern the overall behavior of the structures. And the two type of stress unit is used. One Adobe, which is standard size. And for the extruded adobe, we have customized for our reduced scale model. And there are two types of mortar. That is one used for along with the adobe brick, another with extruded adobe brick. For the compression test, the adobe brick is tested under the vertical orientation without having any interface on the surface, and the two mortar composition is tested with cylindrical samples. And the difference in the compressive strength is due to the composition of the material and the manufacturing process. Similarly, the flexural test is carried out with the 3-point bending test, and the maximum force at failure is used to calculate the flexural strength. As the failure is from the bottom part of the brick, which is brittle in nature, and so the flexural strength can be equivalent to the tensile strength of the brick unit. Another test was done with a sandwich sample. So we tested by fixing one of the brick and applying load on the other brick in order to determine what is the shear resistance. This technique can be also used while optimizing the composition of mortar, which is very relevant in the field applications as well. Here we can see the value for extruded brick is lower as compared to adobe because of the surface rugosity of the brick unit itself. Next, 5 wall samples were prepared, 3 with adobe brick, 2 with extruded adobe brick, and the dimension of this wall was inspired from the previous research work. And we have like on the bottom and on the top, we have a concrete part which is used as a support and as a load application. All the samples were prepared with a random speckle patterns in order to carry out the digital image correlations, and the result obtained from the measurement sensors and digital image correlation is analyzed. So as mentioned earlier in the timeline, we had developed everything for the quasi-static test, but unfortunately fire destroyed everything. And to continue the work, we developed another setup, reaction frame setup, which is driven by electrical jack of capacity 40 kilonewton, and the 4 bar indicated as T1 to T4 is used to apply the initial pre-compression load on the sample, which helps also to prevent the initial rocking moment and transfer the shear force in the shear plane. And all the tests were carried out in displacement control mode, and the same loading was applied for each wall. So let's look at one of the video of the test. So here we can see the load is applied on the top part, and we have a force sensor measuring the applied force, and there is a 2 LVDT attached at the bottom and at the top measuring the relative displacement, which is used for further analysis. So the result from the force cell and the relative displacement is used to obtain the hysteresis curve, and the red line indicates the curve envelope, which is used for further other analysis as well. Here we can see with the application of seismic band, both peak force and the corresponding displacement is increased. Similarly, for extruded brick also, we observe higher value for the peak force and the corresponding displacement. That means with the application of seismic band, both this parameter of the peak force and the displacement capacity is enhanced. Next, for calculation of modulus of rigidity, the same curve envelope is used to obtain the shear stress strain curve, and the second modulus is calculated at the maximum level in both directions, in the positive and the negative loading direction, and the mean value is taken for each case, which ranges from 4 to 7 megapascal. Another calculation is made for the stiffness degradation. For this, the stiffness at same level of displacement in both positive and negative direction is used to measure the slope between that 2 points in order to obtain what is the stiffness at each level of loading or displacement limit. And here we can see with the application of seismic band, both the modulus of rigidity and the stiffness degradation rate is modified. Next, in order to characterize the behavior of shear wall, bilinear idealization is made with the help of equivalent energy elastic plastic method. In this method, the failure limit is measured at 80% of peak load in the post-peak phase, and the initial stiffness is measured at 40% of the peak load, which provides the yield force limit, taking into account the equivalent energy dissipated until the failure is reached. So bilinear idealization curve is developed for both positive part of the envelope curve and negative part. For both wall, we observe that the capacity and the ductility limit is enhanced with the application of seismic band. Next, energy dissipation is calculated by taking the area under the curve, which accounts for both kinematic and the thermal energy dissipations. And here we see with the application of seismic band, the total energy dissipation is also increased. The next, for calculation of equivalent viscous damping ratio, we have used hysteresis curve, and the energy dissipated per cycle is equivalent to that of viscous damping, is the principle which is used for calculation of equivalent viscous damping. Here we have used full cycle approach, and the result is compared for different different configuration of wall. Here we see with the adobe wall we have relatively comparable nature of curve, but with the case of extruded, which is relatively smooth surface, we see significant difference in the viscous damping ratio value. Next, the qualitative analysis of the final crack. Here we see the red box indicates the location where the crack went through the brick unit. It is because of the lower tensile strength of the adobe brick, which created a failure to pass through the brick unit. But with extruded, which has got higher tensile strength, all the failure was between, at the interface between the mortar and the brick unit in both the cases. Next, with the help of digital image correlations, we are able to understand what is the crack point and the crack propagation path. And here I have compared the result at one of the relative displacement, where we can see with the help of strain field, the strain concentration indicates the location where there is potential chance of crack generation and the path of crack propagation. With the application of seismic band, we can see the number of the concentration point is minimized, and the path of the crack propagation is also modified. Likewise, for extruded brick also, we have measure the stress during different loading cycles, and here I have only taken the two images which was taken at relative displacement of 10. Here we can see with the application of seismic band, the stress path is different, and the seismic band helps also to modify the path of the crack. Next, scale 3 at building. I was involved in developing the SEC table. There were a lot of issues which was tackled and which was resolved, but unfortunately after the fire nothing was available. And we are really thankful for FCBA for providing us opportunity to use their SEC table, and also the financial support from the insurance. And it was a really hard work of our entire team during the pandemic, who made successful like all this three house model, which was a real challenge for us. And the capacity of the SEC table is very important in order to determine the size of the structure that has to be tested. So in order to design what should be tested on this SEC table, we consider the capacity of the SEC table available at FCBA photo. And we decided to use half-scale reduced model for 3 different configurations. The dimension of this house was adopted from the DODBC guideline, and a simplified model was chosen in order to compare the behavior of different band materials. And the structure was also made symmetric with the application of 2 windows and 3 doors in order to prevent the torsional effect. All the dimensions of this house was modified as per the Cauchy law, and the earthquake signal that was tested was also modified as per the scaling factors in order to have the same effect on the structures, reducing structures. And finally, the result obtained from the measurement sensors and with the application of DIC has been analyzed. But before moving ahead with the result exploration, let's look at the specimen preparation stage. So 3 houses were prepared, with only difference with the application of band at 4 different levels: sill, intermediate, lintel, and roof. All these houses were prepared simultaneously, on the 3 metallic frame. We had help of 5 students for 1 week, master student who helped us to during the construction work, and like all the 3 structures were simultaneously built with the application of mud mortar and extruded Arabic brick. And this structure was left for drying for approximately 3 weeks before we started applying spackle patterns on each surface for digital image correlations. And we also developed a new setup in order to move the sample from the floor level on to the table. So here we see the process of moving the sample from the floor onto the table. So after placing the sample on the table, all the measurement sensors were installed and the test was carried. So for each house, we applied 5 different level of loading, starting from the lower to the maximum. This one is at the final stage of loading without band structures. All the structures had 2 type of measurement sensors. Accelerometer was placed on the top of the structures on the corners, and outer plane wall had 7 drawing wires displacement sensor, 5 along the midline of outer plane, and 2 at the corners, 6 and 7 at the corners of the outer plane wall, which is also used for the validation of the digital image correlation. For the imaging setup, we had 2 camera setup, one high-speed camera recording the image of in-plane wall, and another 2 camera for stereo vision system recording the image of out of plane and in-plane both. Here, most of the analysis has been made with the help of image captured using the high-speed camera, which was recording the image at 1,000 frames per second. For global structure response, all the structures were tested with a white noise signal before we start the test. And after each loading cycle was completed, we applied another white noise to measure the difference in the fundamental frequency of the structures, which helps us to indicate what is the extent of damage after each loading cycle. Similarly, the amplification of acceleration was measured, taking the average value of each acceleration measured by the 4 accelerometer placed at the corner of the structures. And here we see with the help of seismic band, the damage rate is also modified, and we have a lower amplification because of the sliding at the interface between the seismic band and the other unit. Another calculation was made for equivalent viscous damping. For this, half power bandwidth method is used, which takes into account the 2 frequency on the post and the peak value. So here we have compared the average value of equivalent viscous damping, and we find the comparable results for all the 3 structures. The qualitative analysis is shown here after the final loading cycles, and the red box indicates the location where we have a maximum damage. When we compare the 2 structures with the application of seismic band, we see the damage even after the 5th loading cycle was repairable, and the building was still standing still without having a major influence of getting into complete collapse. Next, for digital image correlation, it is very useful in order to find the displacement field throughout this sample, and we can pick individual points in order to make the analysis. So here I have compared by taking the major principal strain, which also helps us to see how the crack has been generated at different loading cycle and how it has been propagated during the loading cycles. Here we see the crack that was generated in the upper part is moving on the bottom sections without having any band, but with the band the strain is concentrated at the band level, and it prevents the propagation of the crack from each interband section. Another for hysteresis energy dissipation, I have also used the result obtained from the digital image correlations, and I have taken a right part of the structures and divided into 4 different sections separated with the band level. And for each band level, the force value is calculated taking the average accelerations, and the relative displacement is measured by taking the difference between the top and the bottom part to generate the hysteresis curve for force and the relative displacement. But to understand this hysteresis curve, it is very complicated. So in order to simplify the work, I decided to discretize the result in 1 second time interval, and then the area under the curve is calculated for each time second. So here we plot the cumulative energy dissipations with respect to the relative displacement, cumulative relative displacement, and for each interband sections we have made a calculation for this behavior. And when we compare the result for different interband level sections, where we see with the band level interband level 3 there is a maximum energy dissipation, and with band level 4 we have a least cumulative energy dissipation. It was same for all the 3 structures. And next, it was interesting to see what is the overall behavior of in terms of energy dissipation. For this, I added the energy dissipation at each interband level in order to compare the result for 3 structures. And here we see with the application of seismic band, we have more cumulative energy dissipation. Next, analysis was made for the sliding at the interface. For this also, I have divided the incline wall into 12 components separated by band level and also with the openings. And the sliding at the interface is calculated taking the displacement element. And here we see the maximum displacement is obtained at lintel level, and the minimum is at roof band level, in both cases of timber and RC band. Next, for outer plane displacement, I have used the data from the drawing wire displacement sensor, and here the result is plotted with respect to the maximum relative displacement that is obtained at the top of the wall. And here with the application of seismic band, the maximum displacement is also reduced at each level. So for the conclusion, I have divided into 2 different parts for the static and the dynamic. Here I have compared the peak load capacity for different configurations. Here all the results has been normalized with respect to the wall without band. So with application of timber seismic band, there is 6% higher peak load capacity, and with the use of RC band, we have 29% of increase in the peak load capacity. Similarly, the ductility also is compared with respect to a different configuration, and here we see the ductility also enhanced with the application of seismic band. Next, for energy dissipation also, we have increase in case of energy dissipation with the application of seismic band. For the dynamic test, we have increased in the energy dissipation with the application of seismic band. There is 34% increase with the application of timber and 46% increase with the application of RC. In both the structures, even after the 5 loading cycles, there were repairable damage and the structure was still standing. So both structures help to control the crack propagations. So for the main conclusions from this whole experiment is with the application of seismic band, the seismic characteristics of the structure is enhanced, and both structures with the application of seismic band was still not completely damaged, and it was in the extent of repairable limit. That means the main objective of the house is to prevent collapse and save life, which was achieved by the application of both seismic band. And we can also see there is a difference between the performance between the timber band and the RC band, which is because of the difference in the size of those two types of band. And with the help with the timber band, there is a possibility of we can enhance the performance of timber band, but for RC band there is no other way we can modify it in order to have better performance. And also with the RC band, we need more time in order to prepare the sample, and we need a formwork of timber in order to make the concrete band. So there is 2 different scenario for RC and timber band. And with the help of different analysis, we obtain if there is a chance of having only few number of band, we can recommend using lintel band, at least lintel band, or then we can increase the number of band if we want to apply the sea level band. This research work, we have quantified the performance in terms of technical characterizations, but the choice of this type of material also should contain the economic and the social impact, which has to be incorporated in the context of interdisciplinarity. So the perspective of this work is, as mentioned earlier, the behavior and the performance of the timber seismic band can be enhanced, and so more study has to be carried out in order to see the influence of changing the dimension of the timber band. And also another research should be carried out in order to see what is the influence of seismic band in modifying the slenderness ratio for out-of-plane wall. And the approach that was taken in this work could be also used to study the different other materials that is used as a seismic band. For instance, the bamboo or sugarcane materials, or the geomesh that is used in order to separate different level of sections could be used in the similar approach and studied. For the mechanics perspective, we applied 5 level of loading with increasing patterns. But what could be influenced if we apply directly the maximum loading for the structures without gradually increasing the loading should be interesting to see. And also for our case, we had fixed shear normal axial stress for shear wall test, but the influence of varying the normal axial stress could be studied. Another thing which could be interesting to see is to investigate the influence of the drying period of time for different wall configurations. For the socio-technical aspect, the quality control in the field is very difficult, and there is a lot of variations in terms of how it is applied. For instance, the placement of RC reinforcement bar is different, and also the configuration of the timber is different in the field. So it would be interesting to see what is the influence of having different configurations and how it can influence the overall behavior of the structures. And also the next interdisciplinary work which could be interesting to see is to see what is the adaptation on the socio-technical aspect in the community, where our local partners and various stakeholders could play an important role in order to disseminate this information in the site and see how people behave or how they respond in order to adapt this technology. And also another thing is to develop a tool which takes into account the cost and the durability and the other many aspects of social and human science in order to provide a tool for a decision maker to select what material should be used and what could be their performance, whether it is always reliable to use only RC or the timber. It would be a choice with different parameters, not only with technical part. So there is many other things that has to be developed. Talking about the main contribution from this work, 3 scale of experimental campaign was done in order to study the seismic response of the structures, and it was also used for the validation of numerical model for another PhD. And after validating this numerical model, it would be interesting to carry out the parametrical analysis to understand more what would be the response by changing the dimension of the band or by changing the position of this band, which could be also an economic way to understand and study this behavior. Another contribution was we developed a sec table and reaction frame. Even though I was not able to use the developed sec table, we know all the ingredient, how we can redevelop it. So we know what should be checked while making it again to make it functional. Another development was we designed a new method in order to construct the house outside the sec table and move it before the test. So 3 houses was tested for, and the sec table was used only for 6 days. So we could save a lot of time in order to utilize the sec table using the same method. And also another contribution from my work was introduced an innovative method of applying stackle patterns on the large surface, and which could be used for both the high-speed camera and stereo vision camera system, which would be really good opportunity for different other tests. And for past 3 years, these are the list of journal articles, conference articles, and chapter in the book and research catalog developed. And finally, I would like to thank various people on the site and behind the scene who helped to achieve the goal of all this project in multidisciplinary aspect. Thank you.